Hello Year 10, I'm going to talk you through the work that you've been doing in school this week. So we'll start off with a look at the learning objectives of what you're expected to know from the specification. I'm not going to go through all of it, but I suggest you read it to make sure you've understood it. Okay, so most important thing to remember about radiation is that radiation is a truly random or spontaneous process. There's no way of predicting when an atom is going to decay. And there are in fact three different ways in which it can decay. We've got alpha decay, we've got beta decay, neutron decay, in fact four, sorry, and we've got gamma decay, and we're going to talk about those in a moment. So as we've mentioned, and is on the front page of the booklet, there is in fact lots of different types of radiation and lots of different ones that we've got to consider. So we'll start with the heaviest, which is the alpha radiation. Now alpha is a helium nucleus, which means it's got 2 protons and 2 neutrons, but does not have any electrons. So it's a nucleus without the electrons in the shells around it. And that means it becomes a 4-2 helium 2+. That's its symbol, where the 4 tells you the atomic mass and the 2 tells you the atomic number. So you can work the information out. And the 2+ tells us there are 2 protons that have no electrons to neutralize them. Now, because the alpha particle is the biggest particle, it actually has the least penetration ability, so the lowest amount of penetration, but because it has the most positive charge out of all of our, positive or negative charge, out of all of our different radiations, it has in fact got the greatest ionization potential, where ionization means that it wants to steal electrons. So alpha is the big, heavy part of radiation, and it's the one that has a helium nucleus that's quite big, 2 protons, 2 neutrons, no electrons. It's a 2+ because it has no electrons, very low penetration, it's not able to get through paper, and in fact very, very high ionization, which means it steals electrons very quickly and turns into helium gas. The next two are very much linked. We've got beta minus and we've got beta plus. So beta minus is a single electron that's not emitted from the shells, but is emitted from the nucleus. So during the decay, the single electron is lost from the nucleus when something happens inside, and we'll talk about that a little bit later on. And when we write down beta minus in its symbol form, we've got a 0 mass, because remember electrons have very, very little mass, 1/1800th of a proton or a neutron, but -1 because it's a -1 charge. So beta minus is quite often found, and it has a medium penetration and a medium level of ionization. And we call it medium because it's in the middle of alpha and gamma, and we'll see those two extremes, so we'll talk about gamma in a moment. The next one we've got is beta plus. It's very much like a beta minus particle, but this time it's a positive electron, which is called antimatter, so the opposite of matter, which is everything around us. And because it's antimatter, the opposite of matter, it's a plus charged electron, and we call it a positron. So you see exactly the same symbol as beta minus, but we've got a 0 and a +1 underneath. Now that also has the same penetration and ionization ability as the beta minus. Now the last one we're going to talk about on this section is gamma. Gamma is an electromagnetic wave, so it's not a particle, it's a waveform. Remember the electromagnetic spectrum, which is radio, microwave, infrared, visible light, ultraviolet, X-ray and gamma ray. Well, this is gamma, so this is part of that. It has no mass, it has no charge because it's a wave. But it has very high penetration ability. In other words, it can, because the wavelength is so small, it can get through objects. It's not stopped very easily. But because it has no charge, it has a very low ionization ability, so it's not likely to knock electrons off. Okay, so hopefully you've seen this diagram before, but if not, let's talk it through. Alpha particles will only travel a few centimeters in air, and they will be stopped by paper. So if we're looking to check whether we've got alpha particles, we can put our detector the other side of paper, and if the count has dropped from when there's no paper to when there is paper, then that must have been alpha. Beta particles are going to travel a few meters in air. They are moderately ionizing, but they can also be stopped by 3 millimeters worth of thick aluminium. So just having that metal there means that the beta particles are being absorbed into the sea of delocalized electrons, which is what you might have learnt about in your chemistry lessons. And finally, gamma rays can travel a few kilometers in the air. They're very weakly ionizing because remember they have no charge, and they will need several meters of concrete to stop them, or some thick lead. So again, if you want to detect gamma rays, you're going to have to check with nothing and then check with a piece of lead between. And if the count has dropped, then you've detected gamma rays. If you do the same with aluminium and the count has dropped with nothing, and then it's dropped when you put it behind aluminium, then that will have, then the drop there proves that you have beta particles. Okay, so let's talk about what happens to the nucleus when these decays happen. So when we have an alpha particle decay, we are losing 2 protons and 2 neutrons from the nucleus. So the nucleus is dropping by the number of protons, number of neutrons. So in fact, its mass number decreases by 4 and its atomic number decreases by 2. And we've seen this as real exam questions, so really important to learn that because it's a 4-2 helium-2 plus nucleus. You're losing that from the nucleus. From the nucleus it's decaying, so therefore the mass number decreases by 4, the atomic number decreases by 2. We'll come back to the 2 beta ones in a moment, but let's talk about gamma. So gamma is a loss of energy, and because it's only energy that's being lost, there's no change to the nucleus. So the nucleus that's emitting gamma would have had lots of energy. When it loses that gamma, then it has less energy and it's being lost through that electromagnetic wave. So there is no change to the nucleus that's emitting gamma. So if I had barium to start off with, I'm going to have barium after the decay. However, if I'd have had barium to start off with alpha, I'm going to have a different element after the decay because we've lost 2 protons. Now, beta minus and beta plus, these are both higher. So if you're not doing higher, don't worry too much about this, but hopefully this will make sense. In beta minus, it's that some of the subatomic, or one of the subatomic particles inside of the nucleus has changed. So in beta minus, it's where a neutron decays to a proton and in doing so emits an electron. So it's not being lost from the shell. That's really important to remember. You're not losing anything from the shell of that atom. It is that a neutron has spontaneously changed to a proton and emitted an electron. And beta plus is where we are a proton changing to a neutron, and because the charges are different, we're going to emit a positron. And again, we're not losing anything from the shell, it's what happens inside the nucleus itself. Okay, so getting on to what kind of we want to talk about here is this idea of how the nucleus changes and how we can do these radiation decay equations, which is what we're doing here. Now they look really complex, but hopefully you'll see after we get to the end of this that it is just balancing 2 very, very simple equations. So here we've got radium-226 and it's going to decay through a helium-4-2, which is an alpha particle decay. Now, the most important thing we have to do is to make sure the top number, the atomic mass, is balanced on both sides of the arrow, think of that as an equals, and that the atomic number is balanced on both sides of the equal. Again, think of that as the arrow. So here I've got 226 is equal to 4 plus an unknown. Well, hopefully you're realizing that 222 plus the 4 will give me 226. So that top number of our last element, of our unknown element here, is going to be 226. Now we'll do the same for the bottom number. We'll do that in green. So here we've got 88 is equal to 2 plus an unknown. Well, hopefully you've realized that 88 minus 2 leaves us with 86. So we now have our 2 numbers for our elements. We're going to check them, check that that makes sense. So 226 is equal to 4 plus 222, which is true. And 88 is equal to 2 plus 86, which is also true. So how would we find out what the element is? Well, we'll go to the periodic table, we'll look for the same atomic number of 86 and we'll find its radon. And then in those boxes, we're going to write the answer. So it is radon 222, which is 222, 86, radon. So that's an alpha decay, balancing the top and balancing the bottom numbers. So balancing the relative atomic mass and balancing the atomic number. Okay, what about a beta minus decay? Well, a beta minus decay is again very similar. So we'll start with the top number. So we've got 90 is equal to 0 plus an unknown. Well, hopefully you realise if you've not lost any, it'll still be 90. So my atomic number will be 90 at the top. My relative atomic mass. The atomic number, however, will be 38 is equal to minus 1 plus an unknown number. Now, if you think here, because we've got a minus 1, we're going to have to add 1 to get to 0, and then we're going to have to go to 38. So that means that we now have 39. So my atomic number for the beta minus decay is 39. And once we know we've got that 39, so ignore what's in the box, I'm afraid that's slightly wrong, but once you know you've got that 39, you're going to use the periodic table again. In fact, before we do that, we're going to check, as we always should do. So checking the relative atomic mass, so 90 is equal to 0 plus 90, yes, that's true. And checking the atomic number, 38 is equal to minus 1 plus 39. Yes, that is true. So now go to the periodic table to find the element. And we'll find it's this Y, which is yttrium, because we have the atomic number of 39 at the bottom. So on the final step here, we will write down the answers, which is yttrium 90, and it's got 39 protons. So we've now worked out what happens in a beta minus decay, and we can see that the number of protons has increased from 38, but the number of protons plus neutrons has stayed the same. So therefore we must be converting one neutron to one proton. So that's what's happening inside, and it's emitting that one electron, which is our beta minus decay. Okay, beta plus, let's just do this decay. This is a totally different one. We don't often find beta plus. In fact, we don't find it in nature. It has to be man-made, but it's exactly the same process to work out the number that's missing. So we've got 23 as our relative atomic mass for our magnesium. We're going to add 0, so we'll be left with 23. Atomic number, looking at the bottom number now, we've got 12 because that's what makes it magnesium. This time we're plus 1, so we're going to be left with 11. So whatever the element is, in fact, let's do our check before we do that. So checking the relative atomic mass and making sure we're happy with that. So 23 is equal to 0 plus 23. Yep, spot on. And checking our atomic number, 12 is equal to plus 1 plus 11. Yep, I agree with that. So we've got those two correct. Beauty of physics, you can always check you've got your answers correct in the exam. And now let's use the periodic table. We'll go to the periodic table, we'll look for the relative for the atomic mass of 11, and we'll find its sodium. So now writing down our final equation, we have that magnesium 23 decaying through a beta plus decay, so losing a positron, will leave us with sodium 23. And again, like the previous one, we can see that the total number of protons and neutrons hasn't changed, but this time we've lost a proton, so we must have gained a neutron. Therefore, it's a proton changing spontaneously to a neutron, emitting a beta plus particle. Okay, the hardest one of the lot now, gamma decay. Hopefully you can see my sarcasm when I say that, because this time it's 0, 0. So hopefully you're already ahead of me and you can work out what's going to happen. But 137 is equal to 0 plus another number. Well, that number has to be 137. And looking at the atomic number, we've got 56 plus 0 must equal another number. sorry, 56 equals 0 plus another number, so that other number must be 56. So therefore, and again, ignore the box, I seem to have made some mistakes there, but therefore 137 and 56 is our relative atomic mass and our atomic number. Let's check our results again. 23 is equal to 0 plus 23. Nope, that's totally wrong. 137 is equal to 0 plus 137, and 56 is equal to 0 plus 56. Correct. Ignore the box. That's totally wrong. Must have copied and pasted. So we'll go to our periodic table just to check that we haven't changed the element. We're looking for that 56 as our atomic number. Yes, it's there. So we're going to write 137, 56, barium. And here is our answer, 13756 barium. Okay, so that's, oh no, one more. We've got neutron decay. And in neutron decay, we are losing a single neutron from the nucleus. So here we've got helium-10, so it's 10 protons and neutrons. 2 of those are protons, so we've got 8 neutrons in helium-10. We're losing 1 neutron, so that must mean I've gone from 8 to 7, but I've still kept my 2 protons, so I'm going to have a 9 at the top, or in other words, I've got 10 is equal to 1 plus another number, which is 9. Looking at the atomic number, we've got 2 is equal to 0 plus something. We know what that something is. It has to be a 2. So therefore, I've got 9 and 2. Let's do our check. So 10 is equal to 1 plus 9. Happy with that. And 2 is equal to 0 plus 2. Happy with that. So let's check our final answer. In the periodic table, we can see that helium will have an atomic number of 2. So it's helium still. Writing our final answer now, we know we've got helium-9 2. So there's 9 protons and neutrons, and 2 of those are protons. So that would be our final answer. So this is everything we went through in the lesson in school. So you've now had the same experience as every student who was in school. There are questions on the worksheet that has been uploaded for you in this same assignment. Have a go at them. We'll put the answers up as well so you can check your answers. Let us know if there's anything you don't understand by contacting us through the science email address.